So here we are going to find out the electric field due to uniformly charged rod. Okay, and here we can see this is the uniformly charged rod on which positive charge is uniformly distributed. Okay, let the linear charge density of this rod, that is lambda here. Okay, so at this point P, let this is the point P. At this point P, we are going to find out the electric field due to this rod. Okay, so for this, first of all, let the distance of this point from this rod, that is r. Okay, and now we want to apply the Coulomb's law, and for that we will have to take an elementary charge. So here we are going to take a element of which length is dl and charge is dq, and this element is at a distance small l from this point. Let this point is point t. Okay, so because of this charge dq at this point p, there will be electric field at d. So d, that will be kq upon r square. So we can say k, charge is dq, and the distance of this element from this point p, that is r dash. Okay, and from this right angle triangle we can say that r dash, that will be l square plus r square. So we can replace this r dash by l square plus r square, and as here we can replace this dq from here, dq, that will be lambda into dl. So we can say k lambda dl upon l square plus r square. Okay, now here we can see that there will be two component of this d. First component, that will be d cos theta, which is perpendicular to this rod, and the second component, that will be d sin theta, which is parallel to this rod. Okay, so now first of all we are going to find out the parallel component. Okay, so for that we will have to integrate this d sin theta. Okay, so d, that we have already find out, d, that is k lambda dl upon l square plus r square. Okay, sin theta as it is. Now here, as we can see that tan theta, from this triangle we can see that tan theta is perpendicular upon base. So we can say tan theta is L by R. So from here we can write L, that will be R tan theta. So we can write DL because we want to replace this DL in terms of d theta. So DL, that will be R tan differentiation, that will be sec square and theta. Okay, and there will be d theta also. So we can write dl as r sec square theta d theta, k lambda as it is, and here it is sin theta, and here there will be l is r tan theta. So there will be r square tan square theta plus r square. We can take r square common here, and there will be 1 r here. So 1 r, that will be cut by 1 power of this r. Okay, and there will be k lambda, and there will be sec square theta, and because here there will be tan square theta plus 1, which is sec square theta. So sec square theta cancelled out, and there will be sin theta and d theta only. Now here we can see that we will have to integrate this sin theta. Okay, and the limit of theta, that we can see from this diagram. Lower limit, that will be angle beta, and because this angle is downward, so we will take it as minus beta. Why? Because here we were taking upward angle theta as positive angle, that's why downward angle will be -1, and the upper limit, that will be this angle alpha, which is made by this upper end of this rod with r. Okay, and the beta angle, which is the angle between r and the line connecting to this end of the rod and point P. Okay, so we will put the limits from minus beta to alpha sin theta d theta. Integration of sin theta, that will be minus of cos theta, and here we can put the limits. So this minus sign that has come out, so it will be k lambda upon r cos alpha minus cos of minus beta, and now when we will take this minus sign inside, so there will be E parallel is equal to k lambda upon r cos beta minus cos alpha. So this is the parallel component of electric field. Now we are going to talk about perpendicular component. Okay, perpendicular component. It means now we will have to integrate this dE cos theta. Okay, so here we can see dE cos theta integration, and we will put the limit that will be from minus beta to alpha. And because we have already solved this part, and that came k lambda upon r that we have seen. Okay, and d theta that also was there. So here will be d theta and cos theta, and you can see that how we solved this part. You can see here k lambda dl upon l square plus r square. How we solved it, that we have already seen. Okay, so there was sin theta, and now here it is cos theta. Okay, so now we will take limit from minus beta to alpha. We will integrate cos alpha, which will be cos theta, which will be sin theta, and limits are from minus beta to alpha. So finally solving it, we got here E perpendicular is equal to k lambda upon r. Here will be sin alpha minus of sin minus beta. Okay, so finally solving it, we got perpendicular component of this electric field, that will be k lambda upon r sin alpha plus sin beta. I hope you got it. Okay, if alpha and beta both are equal, if alpha and beta both are equal, then we can say that the point P, that will be at the somewhere at bisector line. Okay, and in that case we can see that E parallel that will be 0. Why? Because cos beta and cos alpha both will have same values, and these will get cancelled out, and there will be 0. So E parallel will be equal to 0, and E perpendicular, that will be E perpendicular is equal to k lambda by r, and here there will be sin alpha plus sin alpha, that will be 2 sin alpha. Okay, so I hope you got this point. I hope you got this topic. Thank you very much.